Hello, I'm Keshav, and today I'm going to talk about the traveling salesman problem and a useful heuristic for solving it called simulated annealing. So the traveling salesman problem is, let's say you have like a couple of cities on the map here, and you want to know what's the fastest way to get through each one, or what is a way to connect all these dots with the least possible distance. And so the only known way to solve this for sure is to just brute force it, and that is just look through every single combination of like how you can connect these dots and just find which one is shortest. But this is first of all very slow, but even worse, it gets exponentially slower with the number of dots you add. So if you want to say look through like 200 cities, solving it by brute force would take longer than your lifetime. So to solve these types of problems, we want to use what's called a heuristic, which gives us a good enough answer. It doesn't have to give us the best thing. And in this case, this problem is known as an optimization problem. And there are many different problems similar to this, but a good way to solve this is with a method called simulated annealing. And to look at this method of solving it, we have to let's start with a simpler example so we know what's going on. So right here, we have another optimization problem. It's just finding the maximum value. And what you can see here is when this GIF restarts is that the red line will start at a high temperature. And what that means is this red line will start searching all over the place to find an ideal solution or a highest value. And what this red line does is at each time step, it has a certain probability of moving somewhere else along this line. And this probability is determined by one, the temperature. So when it's at a higher temperature, it has a greater probability of moving somewhere else, and also how high it is. So the higher up it is, the less probable it'll be for it to go kind of far away, and it'll be rather to stay in the same place. And so what this is doing is, at stage one here, when the temperature is high, it's kind of scanning all over all of these possible values, trying to find what's called kind of a global maximum area. So as you can see, it's looking in this region here where there is a global maximum. And then as it cools down, it's starting to narrow in on a better answer. So as you can see in low temperatures, it starts hanging out more in this area here where the global optimum is. And when it gets colder and colder and colder, you can see that it moves less and less and less and starts settling into the most optimal position. So now if we take this back to the traveling salesman problem, at the high temperature stage, what we'll do is we'll make lots of drastic changes in our path. So at first it'll just be like looking at a random path each time. But as we get shorter and shorter distances, we'll eventually converge to something that has a shorter and shorter distance. And then eventually we'll reach a point where the paths themselves will start just changing in very small amounts. So as you can see in this example here, at a lower temperature, the only things that are changing are like these little tiny distances here, which don't have that much of an effect on the overall path length. And as this cools down, it'll narrow down to the correct value. And so in this way, this is much faster because instead of calculating through every single possible value, we only go through some of them. And it kind of relies on the assumption that near these kind of global optima are solutions which are very simple, which are also very good. And so by just using this probability of staying in the same path or moving based on how short the path is, it'll eventually converge to the global optimum.
So one question you might have about this method is why do we bother with having this random probability of changing this path length, and why do we bother doing all this random stuff? Can't we just find a definite way to do it, just an algorithm that takes us directly to the solution? And while that might seem like a good idea at first, there is one problem with that. And we can start with a simple example here of where that would fail. So let's say we want to optimize this value. That means we want to find the maximum value. So one first idea that we might have to solve this problem is, let's say we start on this left end here, and we just go in the direction where the value increases. So at this point here, it looks like this derivative is positive, so we'll keep moving this way, and we'll keep on moving up and up and up until we get to this point here. But once we get there, we reach what's called a local maximum. And what this means is that the derivative is 0, so the points directly to the left and right of it are going to be smaller. But as you can see, we completely missed the global maximum, so this is not a good method. So that is kind of why we have to have these random probabilities, so we don't get stuck in these local maxima. And another question is, why do we bother with temperature and everything? So the reason that we use temperature is mainly for speed, and if we kind of start at a low temperature, sure, we will eventually get to the right answer statistically speaking, but it might take longer because we might just be stuck in this area for a long time, but eventually we will get here. And the reason that we will kind of eventually get to the global optimum has to do with the way that this algorithm is structured, and namely that there's always a probability that we will stay in the same location. And so, for example, if we do reach the global maximum, there's actually quite a high probability that we say, oh, this is the maximum, let's not change our location, let's stay there. And this does something, and this gives it a property called ergodicity, and this kind of means that any point on this curve can be reached by any other point on this curve with a certain probability. So there's always a probability to go from like point A here to point B here. And because this point here, called the global max, is the one that has a maximum probability, this point, statistically speaking, will be the one where this line goes to at the end. So to see simulated annealing in action, let's look at the traveling salesman problem again. But here, we are trying to find the shortest path between 500 or so AT&T offices throughout the United States. And this is something I made for a scientific computing class a year ago. And this uses the same simulated annealing algorithm that we just talked about. And as we can see, the final answer we end up with does look pretty good. And it appears that it could be a lot worse. So now let's look at the total length of this trip versus the temperature. So at first, it looks like the length is very long, and this temperature step here corresponds to basically the time step. So you can think of it as like an inverse of the temperature. So a low temperature step means a high temperature, and a high temperature step means a low temperature. So initially, the length is kind of long. It's about 80. And then as we increase the temperature, we can see that it starts settling into what appears to be a pretty optimal path. And so I guess this is kind of like evidence that it works, because we can see that it does converge to something. And because of how we explored all possible paths in the high temperature region, we can be pretty sure that this is the global maximum, or at least close to the global maximum. So yeah, this algorithm does work, as you can see. Thank you for listening to my presentation.